Hello students, in this video we're going to talk about the probability tree model some more, as well as to revisit the sample space. I hope you realize by now that drawing or designing the correct sample space is really going to help us tremendously in finding the probability of whatever that we're looking for. If we design the wrong sample space, then it's going to be very, very difficult to get whatever the final probability number is. So there are a couple of things I want to emphasize on the designing of a sample space. The first one is mutual exclusivity. It means that all the outcomes have no overlap with each other. In other words, there's no particular incidence where an outcome can be counted or the particular result can be counted by both outcomes. Okay, and we'll illustrate that with an example later. The second one is called collectively exhaustion. And collective exhaustion just means that all possible outcomes are included in the sample space. Okay, we have not left anything out. So similar to the video from Mr. Dobovich, collective exhaustion means that we are not miscounting anything. Okay, we haven't missed anything. But there's a third criteria that is a highly desirable criteria, but is not a must-have. Okay, so there is a nice to have, and that is we want to have all the outcomes listed in the most granular manner. Okay, you heard of the term granular, means that is really cut up to be very fine in very small pieces of articles. We call that granular. Okay, what I mean is that you want to list every possible outcome in its own separate way, so that you're not lumping things together. And that would allow us to calculate probability much easier. Okay, let's illustrate that with an example. Okay, so we should be somewhat familiar with this example now. This is about the free throws by Washington in one of the NCAA final games. And he went to the free throw line for 3 possible shots. Okay, let's see if we can map that out from a probability standpoint. Let's consider that an experiment comprised of 3 events. Okay, so this is the start of the experiment. He can make or miss the first shot, right? So let's say let's call that a hit and a miss, just so that we have a different character. Okay, so this is his first free throw. And then, okay, and after the first one, he might hit, he might miss. Similarly, he might hit, he might miss, and he might hit, he might miss, he might hit, he might miss, hit, miss, hit, miss. Okay. Now remember, he's a 72% free thrower, so therefore let's use 0.7 just for simplicity as the chance that he's going to hit it, and 0.3 as the chance that he's going to miss it. So I'm going to label all the probabilities like that. 0.7, 0.3, 0.7, 0.3. Okay, and I've finished labeling all the probabilities for all the branches. And remember, the sample space is simply listing out all the 3 events together. So for example, the very top one, this would mean that he hit all 3 shots, HHH. The second one would be HHM. He hit the first 2, missed the third one. Okay, and I've listed them all here. Now, to calculate the probability of each outcome, we're going to multiply all the probability numbers along the branches that lead to that final outcome. So, for example, HHH would be 0.7 times 0.7 times 0.7. And I'm going to do the same thing for the rest. So the second one is 0.7 times 0.7 times 0.3. Okay, so I've listed out all the rest, and I've also calculated by multiplying those numbers. So for example, the chance of him hitting all 3 throws would be 0.343. The chance of him missing all 3 throws would be 0.027. Okay, so with that, now we can start answering certain questions by simply looking up or adding up those numbers. Okay, so now that we have the sample space and all its associated probability all tallied up, we can answer some pretty complex probability questions. So let's say question 1, what's the probability of him hitting at least one shot? Okay, so what are the outcomes that would qualify for him hitting at least one shot? So let me use it in orange. Okay, clearly disqualified, disqualified, this. The only one that wouldn't fit the criteria would be he missed all 3 shots. So all I have to do is simply just add the ones that I've check marked. So 0.343 plus 0.147 plus so on. Now notice that I can also do a 1 subtract the one that he missed. Because the thing about probability is that if you add up all the probabilities in the sample space, it always equal to 1. So the summation of all outcomes must always be equal to 1. That's one of the properties. Okay. In other words, one of those outcomes must happen, right? So therefore, if you add up all the probabilities, it has to be equal to 1. Okay. One of the outcomes must occur. So I can just do 1 minus 0.027, which would give me 0.0973. Okay? Sorry. 0.0973. Okay? So of him hitting at least one shot, very high probability. Okay? Now let's take a look at the second one. The second one says, what is the probability that his team wins the game? Now remember, the scenario says that they're down by 2 points. So if they're down by 2 points, the only way he can win the game would be by winning 3 points. That means he has to make all the baskets. So that would be the same as the probability of H. Okay? And that would be 0.343. Okay, so the probability of him having his team win the game would be 0.343. What is the probability of the game going to overtime? Well, going to overtime means that he make at least 2 shots, okay, or exactly 2 shots. Okay, if he makes 3, then he would win it. But the only way the game can go into overtime is that he makes at least, precisely 2 shots. So let's use yet another color. Let me use green this time. So where does he make exactly 2 shots? Well, this would be 2 shots exactly. This would be 2 shots exactly. This would be 2 shots exactly. And is there another one? No, looks like that's it. Okay, so there are only 3 outcomes that would have 2 shots. So the probability of going to overtime would be equal to 0.147 plus 0.147 plus 0.147, which is equal to 0.441. So there's a 44% chance that the game would go into overtime.